Hello, I'm Jo Fay, and this is a SwissInfo podcast. SwissInfo is the multilingual and international public media company of Switzerland. In 2010, the European Organisation for Nuclear Research, known as CERN, started smashing particles inside its Large Hadron Collider. This 27-kilometre underground ring near Geneva is the world's most powerful particle accelerator. Now scientists at CERN are planning to build an even bigger collider.
Moment historique, mise en marche du plus puissant briseur d'atomes du monde. Un jour de gloire pour la pacifique science atomique européenne.
Particle colliders have been used since the 1950s to help physicists explore the laws of the universe. In 2012, scientists working on CERN's Large Hadron Collider achieved a key breakthrough with the discovery of the elusive Higgs boson particle. This broadened our understanding of how particles acquire mass.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
That was the British physicist Peter Higgs, right after the discovery of the Higgs boson in 2012. For this, Higgs and his team won the Nobel Prize. But what is this small particle called the Higgs boson, and what can it tell us about the universe? To answer this very big question, I've got our science journalist Simon Bradley here with me. Hi, Simon.
Hi, Jo. The Higgs boson was a very important discovery, as it was said to be the last missing piece of the so-called standard model of particle physics. This is what gives all elementary particles mass, allowing for the existence of matter. Scientists say it's a fundamental unit, or quantum, of the Higgs field that all particles must pass through. Some elementary particles, like the photon, slip through unhindered. They are massless. Others, though, must struggle, a bit like a fly trapped in treacle. Through Higgs boson interactions with the so-called Higgs field, elementary particles gain their observed masses. The more strongly they interact with the field, the larger their masses. The Higgs in its field had never been conclusively detected before 2012. The Higgs boson was created at CERN in a particle collision inside the Large Hadron Collider. But you have to watch very carefully, as right after collision it transforms or decays into other particles that can be found in particle detectors. Thanks to careful analysis of enormous amounts of data, they uncovered the particle's faint signal and confirmed its existence and that of a new force field, the Higgs field, permeating all of space.
Impressive stuff already, but of course now scientists at CERN are planning to build a much bigger collider. You visited CERN towards the end of 2023. What did you find out while you were there?
So my first appointment was with Mike Lamont, the director of accelerators at CERN. He's strongly involved in the planning of the Future Circular Collider, or the FCC. Why do we need a future circular collider when we have the LHC?
Good question. There's some big unanswered questions about the universe out there, which we feel we will not be able to answer with the LHC in simple terms. So the first phase of the FCC is build a tunnel and then put in an electron-positron machine. So this is enabling us to kind of do dedicated large-scale Higgs production, and as the physicists put it, study the hell out of the Higgs and really kind of look for any deviations from the standard model, our kind of present understanding of most of the universe we see around us, and try and get a handle on some of the big unanswered questions that way.
What is the end goal of the FCC?
We build these machines to explore the nature of the universe. And if we look out there at the moment, the big unanswered question is dark matter. There's undisputable evidence from astrophysics observations that it's out there. It's shaping the large-scale structure of the universe. It's affecting the rotational speed of galaxies, etc. So we know it's there, and we really have got no idea what this is for the moment. And we're not even too sure what mass scales this dark matter is taking. And of course, this is part of the adventure of going out into the unknown, exploring further.
A quick note on the scale of this new collider. As mentioned before, the current Large Hadron Collider measures 27 kilometres in circumference. The FCC will be over 90 kilometres, so 3 times larger. Can you explain the phases? There'll be a first phase and then a second phase. What will change?
But the first version, electron-positron machine, will be a warm machine. So these will be warm magnets. So there's a full physics program there on the electron-positron machine. Now that would take, say, 10 to 15 years to fully execute. And then we take out the accelerator and we put in a superconducting proton collider. These superconducting magnets have to be very strong, cooled with liquid helium, very high magnetic fields, technologically very challenging. The total energy in a proton-proton collision in the LHC at the moment is 14 TeV. The FCC design collision energy is 100 GeV, so really stepping up, as I say, by almost a factor of 10 to, for the moment, unimaginably impressive energies.
Everything about this future project is big, including the timescales. After more than 10 years of construction work, Phase 1 of the FCC would run from 2045 to 2060. That would be an electron-positron collider. Then, following another decade of dismantling and reinstallation, a second, even more powerful particle accelerator, which collides protons, would run inside the FCC tunnel from 2070 to 2090 and later. So like with the Large Hadron Collider, the future circular collider will be underground. The circular tunnel around the city of Geneva on Swiss and French territory will have 8 surface sites from where the experiments and teams of scientists can be orchestrated and which will give access for maintenance. We met the FCC project leader, Michael Benedict, who showed us one of the future surface sites for the collider.
We're here at in France, just north of Geneva. One of the entry points, the surface points, will be here. How big will it be?
It will be typically 4 to 5 hectares per surface site, and in total there are 8 such surface sites. So it's essentially the field that you can see here.
This whole field
this
will be
whole
taken.
field here will be taken, not up to the forest, but up to the middle, roughly.
And for the feasibility studies, you're looking at environmental aspects and geological aspects and seismic aspects, I understand. Could you maybe elaborate? What are the environmental aspects you have to consider for such a project?
We are using the avoid, reduce, compensate principle. This means you try to develop a project by avoiding as many environmental difficulties, risks from the very beginning. Only if you can absolutely no longer avoid, you try to reduce by designing the project, by choosing surface sites in optimum locations. And the last step would be to compensate for any impact. Now, what we are doing is we developed together with Switzerland and French host state authorities a risk matrix to understand territorial constraints, to understand, for example, urbanistic plannings, to understand existing or future planned infrastructures in terms of transport and access, to understand, of course, location of protected zones. These can be Natura 2000 zones, or these can be water reservoirs that are relevant for drinking water in the longer term. These can be natural parks like the Jura Mountain, for example. And in choosing an ideal implementation, you try to minimize the risk by taking into account as much of these constraints as you can. Yeah? Now we are moving into an exploratory phase. We have identified an ideal trace and the ideal location of surface points. And now we are starting with environmental studies to understand the fauna. Exactly, to understand already the initial state. This is the step one.
Michael explained that CERN is talking to local people and officials about how they can work together and share the benefits of a future FCC. One idea, for instance, is to use the heat generated by the collider to heat local hospitals, schools and homes. Digging a huge underground tunnel can raise fears about earthquakes. I asked Michael whether this is something CERN is worried about in this particular region.
When you look at the geology, is to large extent dominated by a molasse layer. This is a soft rock layer that usually
positive, then.
That is positive. Yeah, that usually contains no water at high pressure, for example. That usually contains no karstic structures. So this is an ideally suited terrain or geology for constructing a tunnel with tunnel boring machines in standard technology.
Michael then takes us to a nearby surface site of the existing collider.
Hello.
The FCC surface sites would be similar.
This is one of the surface sites of the LHC machine, and this is the point 8 of the LHC. There is an experiment roughly 80 meters underneath, where the particle beams of the LHC are colliding.
The LHC is below us. How far below is it?
Well, it's, I think here, don't quote me, but I think it's one of the most shallowest point, maybe 50, 60 meters
so 60
below
meters,
ground.
We have particles firing around.
Yes.
And
they are colliding exactly here under these points.
Yes.
And around the collision point there is a big detector that is built. It's called LHCb. And the surface buildings that you see here are needed to supply the experiment with infrastructure, electricity, cooling, cryogenic gases and cryogenic liquids.
And so for the FCC, you'll have 8 of these similar structures. Is that correct? Similar sites.
For the FCC, we will have 8 sites comparable to the one that you can see here. Yes.
Okay. We already have the LHC at CERN. I mean, why do we need a future circular collider?
Well, the LHC has discovered in 2012 the Higgs particle, which was the missing element in the standard model of particle physics. And with this discovery, this model has been completed to some extent. There are, however, several very fundamental questions about the universe and about nature and about our existence. And the smallest particles and forces that hold us all together and that are responsible for the universe in the form as it is. And these questions remain still open. One of the key words in this context is, for example, dark matter. It relates to distortions, let's say, of motions that can only be explained by the existence of a sort of matter that we do not see, that we do not understand. We cannot explain the force. We cannot explain the nature of this matter. And this makes up a huge percentage of the universe. Another of the big questions is, for example, the imbalance between matter and antimatter. You, me, the field around us, everything is made out of matter. And in the Big Bang, at the beginning of the universe, there was creation of matter and antimatter in the same quantities. So now the question is open, where has this antimatter gone? Where is the asymmetry between matter and antimatter that is responsible for us being all made out of matter?
Thanks for taking us along with you, Simon. The timescale of this project is really something, isn't it? Some of the experiments won't start there until 2070. I'm lucky if I have something planned for Christmas. I mean, let alone so many years in the future.
Yeah, it's a very long-term physics adventure in search of answers to fundamental, unanswered questions about the universe. It's amazing. After the feasibility study, the CERN member states will first have to approve the project. That will be in 2028. Should they decide to move ahead, construction of the FCC would start around 2038.
Right, so most of us, and even most of the physicists who are planning this gigantic project, we won't even be around to hear the answers to many of those big questions.
No, they won't. But in the meantime, there are plenty of other things going on at CERN, and we will definitely keep you informed about any progress made there.
Brilliant. Thanks a lot, Simon. If you enjoyed this episode, please join us next time when we'll be looking at DNA sequencing and how it can be used for investigating biodiversity, just from a sample of soil, water, or air. Today's episode was recorded and edited by our science and video journalist Michele Andina. For more content, visit our website, swissinfo.ch. I'm Jo Fay. Thanks for listening.
Do you want to polish your knowledge about Swiss elections, referendums and political parties, while at the same time learning more about the quirks of the political system in Switzerland? If that's the case, our newsletter course is just what you need. Each week for a month, we'll send you a free installment explaining the most important details of how Swiss democracy works. Our course teaches you who's eligible to vote in Switzerland, what the different parties stand for, how election and popular vote results are implemented, and what distinguishes Swiss democracy from other political systems. Our crash course is interactive, like democracy itself. Your questions will be answered on an FAQ page, and you can debate with other users and share your inputs and opinions. We will also provide links to multimedia articles and videos to help you better understand the Swiss democratic system. Please join us and sign up for the free Democracy Crash Course newsletter at www.swissinfo.ch/democracy. That's www.swissinfo.ch/democracy.